In part 2 of this chapter, we study measures of variation, and the two main measures of variation we study are the range and the standard deviation. We differentiate between the standard deviation for a sample and for a population, just as we did for a mean. Remember, just to review, the standard the mean for a sample is indicated by the notation x bar, and the mean for a population is denoted by the notation Greek letter sigma. Well, similarly, we have different notations for standard deviation of a sample and a population. The standard deviation of a sample is denoted by the small letter s, and the standard deviation for a population by the lowercase Greek letter sigma. Okay, in thinking of variation, we think of that as how spread out the data values are. So variation is a measure of spread. The more spread there is, the more variation there is in the data. If you compare these two dot plots, which summarize random samples of high school students' IQs, the first is a random selection of high school students, and you can see by looking at the smallest value here and the largest value there that there's quite a bit of spread in this data set. However, when you group by grades, you see that there is not the same degree of spread in the data set. And so the first data set has greater variation than the second data set. Notice, however, that both samples have a mean of 100. Just want to point out the round-off rule for measures of variation is the same as the round-off rule for measures of center. Carry one more decimal place than is present in the original set of data. So if the data is whole numbers, you would round to 1 decimal place. If the data already contains 1 decimal place of in the numbers, then you would round to 2 decimal places. But remember, only round final calculations. Do not round in intermediate calculations. Only the final step, the final answer, is rounded. So the range is one measure, as mentioned before, of the variation or amount of spread in a data set. You calculate the range by simply taking the largest x value, the largest data value, which can be indicated by x max or max x, and subtract from that the smallest data value, x min or min x. In 1var stats, the calculator TI gives you those two values, the minimum x value and the maximum x value. And so when you're looking at your 1var stats, you search for those two, min x and max x, and just subtract them. And so the range of this data set would be 10 minus 4.2, which is 5.8. So that's the range. Here's an example of two different data sets which are obtained by looking at the waiting times in minutes for people standing in line. The first situation, there are multiple lines that are going to multiple checkouts. So everyone's standing in a line, and that's where they go. They go to the checkout for that line. These people go to the checkout for that line, and these people go to the checkout for that line. These are the wait times in minutes, so we have 10 values. The smallest value here is 4.2, indicated right here, and the largest value is 10, indicated right there. And you can see that the rest of the data values are inside of this blue box. And this is called a box plot, which you can also get by using 1var stats. And there's a video on Sophia that explains how to get a box plot. So that's the box plot for the first data set. The second data set has all the customers in one single line, but they're waiting to go to the next available checkout. So each person in line, as they come to the front of the line, will go to a different checkout. So there are multiple paths to the checkouts here. And we see that the wait times here, the smallest value is 6.5, and here is that on the box plot. The largest value is 7.7, and here is that on the box plot. And you can see that the rest of the data values are squeezed in between those two numbers. So there's a smaller range, and hence less spread in the data for the second data set. So we have people waiting as long as people are waiting in the other situation, but not as many of them. So it's a little bit better situation if you're the one standing in that line. It just seems more equal. Okay, so another measure of variation is the sample standard deviation. So standard deviation of a set of values, if you're using a sample standard deviation, if the data values are from a sample, we denote that by the small letter s. And again, the best way to do this, if you have a large number of data values, is to just let the calculator do the work. And you can find that standard deviation in the calculator under one var stats. Just remember that you must round that value to the proper number of digits. So if your data consists of numbers with 1 decimal place, you would round this standard deviation to 2 decimal places, and that would give us 1.82 as the standard deviation, and that's the value that we would report. And we would denote that with the letter S because it's a sample value. These are the formulas for sample standard deviation, and this is why I suggest that you learn to use the calculator for this instead of trying to use either this formula or that formula. But I'll run through those very quickly for you. So to calculate the standard deviation using the formula, first of all, using the formula 3.4, the first thing you have to do is compute the mean, and that's why this formula is somewhat cumbersome. First thing you have to do is calculate the mean. So add all these numbers up and divide by the number of numbers that you have. That will give you the mean, so put that number there. The second thing you do is subtract the mean from each data value to get the deviation from the mean. So take each of these 10 numbers and subtract the mean. So whatever you get for your calculation in the first step, take each data value and subtract. Then you'll have 10 new numbers. So each data value subtract the mean. Then you're going to, in the next step, square each of those subtractions that you did. So now you'll have 10 numbers that are the squares of the deviations from the mean. Then you take those 10 numbers and sum them or add them all up. So now you'll have one number right here, one single number. Then you take that number and divide it by n minus 1. N is 10, so you're going to divide by 9. So divide by 9. This is what's called the variance. Before you take the square root, the number that you have is called the variance. If that's what you want, then you would round it appropriately and report it. Before you round it, however, if you take the square root, then you have the sample standard deviation, and that's the final step. And then, if you're taking the square root, after that step is where you would round. So it depends on what you're doing. Round if you want to report the variance, round at this step and report the variance. If you want the sample standard deviation, before you round, take the square root and then round for the sample standard deviation. The other formula is just a little bit easier to use. So to use the other formula, the first thing you would do is figure out what n is, because the other formula has n and it also has n minus 1. So then you know what n times n minus 1 is, so calculate that. In this problem, n times n minus 1 will be 90 because n is 10. The next thing you do is add up all the data values and square that sum. That's what this means right here. This means take all the data values and add them up and square that sum. That's what this is, the sum of the data values squared. You also have to square each data value and compute the sum of the squares. So that's what this means, to add up the square of each data value. So that's what this part of the formula is. So take each data value, each of these numbers, and square them. So you'll have 10 numbers, all the squares of these numbers. Don't round. Take the square of each of these numbers, and then add those numbers up, add those squares up. You have to multiply that times n, subtract this number that you calculated before, and then divide by 90, n over n times n minus 1. That will be the variance. If you take the square root, that will be the standard deviation. And so it's a little bit easier to use the formula in that form. But again, I write a calculator. You can also obtain the population standard deviation from the calculator. That's sigma, and see, the calculator tells you what the population standard deviation would be. It treats the mean as a population mean, and instead of dividing by n times n minus 1, it just divides by n. A little bit more about variance, and we'll cover variance more thoroughly in a later chapter, but the variance is just what you get before you take the square root for the standard deviation. So before you take the square root, the number that you have there is called the variance. The sample variance is called an unbiased estimator of the population variance. We'll have more on this later of exactly what an unbiased estimator is. But what it boils down to is that the sample variance is oftentimes used to estimate the population variance. Probably the most important thing next to standard deviation in this chapter is the range rule of thumb, or in this section of the chapter is the range rule of thumb. So make sure that you understand these calculations. I have a little typo here. That should be 70. I thought I fixed that, but for many data sets we study, most of the individual data values are within 2 standard deviations of the mean. So if the mean of a data set is 100, as in IQ scores, and the standard deviation is 15, 2 standard deviations would be 30, just 2 times 15. So most of the data is between 130 and 70. And the reason is because 130 is 100 plus 2 standard deviations. Remember, a standard deviation in this data is 15, so 2 standard deviations is 2 times 15. 100 plus 2 times 15 is 130. And 100 minus 2 times 15 is 70. And so we say that most of the data that we're going to study is within 2 standard deviations of the mean. Oh, I'm sorry, I need a slide. Here we go. So the range rule of thumb for IQ scores, since IQ scores are normally distributed, we can use this range rule of thumb, and that's the key. The data values must be normally distributed. If the data values are normally distributed, then we have this result, that most of the data is within 2 standard deviations of the mean. So let's see again what that means graphically in a picture. Here's the mean, and here is the length of one standard deviation. In this data, one standard deviation is 15 units long. And so if you're within 1 standard deviation, you're between 85 and 115. And if you're within 2 standard deviations, that means that your data value is between 70 and 130. And notice that's exactly where the hump, which contains most of the data, that's exactly where the hump is. These ends, the tapered ends, which are called tails, these are the tails, and this is the left tail, and this is the right tail. Those tails do not have as many data values. In fact, they only contain about 2.5% here and about 2.5% there. So you can see that the tails only contain about 5% of the data. Most of the data is within 2 standard deviations of the mean. And in this normal distribution, that means about 95%. That's called the empirical rule for data with a bell-shaped distribution. So study this figure in your text. You can see that 68% of the data is within 1 standard deviation of the mean, 95% of the data is within 2 standard deviations of the mean, and 99.7%, almost 100% of the data, is within 3 standard deviations of the mean. There are very few data values that are 3 standard deviations greater than or less than the mean in a normal distribution. One more look at this. 99% of the data is within 3 standard deviations of the mean, and so that means that if we look at 2 standard deviations on either side of the mean, that's a total of 4 standard deviations. So 4 standard deviations is 4 times S. 4 times S is approximately equal to the range of the data. If you think about that, since most of the data is within 4 standard deviations, 4 standard deviations contains approximately the same amount of data as the range does, and so 4S is approximately equal to the range. With just a little bit of algebra, you can solve that for S. Just divide by 4. Here is a very rough estimate of standard deviation for data that is normally distributed. If you take the range and divide by 4, it's a rough approximation of the standard deviation. So there is one more measure of variation called the mean absolute deviation, and here's how it's calculated. This data consists of the number of military intelligence satellites owned by India, Japan, and Russia, respectively. So India has 1 military intelligence satellite, Japan has 3, and Russia has 14. This is as of 2010. The mean of those three numbers is simply found by adding them up and dividing by 3. So 1 plus 3 plus 14 is 18, and 18 divided by 3 is 6. So the mean is 6. The deviations from the mean are found by taking each data value and subtracting the mean. So 1 minus 6 is negative 5, 3 minus 6 is negative 3, and 14 minus 6 is 8. Now if you add those three numbers together, you get 0, which is why we don't add those three numbers together when we're calculating variation. In the standard deviation formula, remember, we take those deviations and square them before we add them together. That makes them all positive. For mean absolute deviation, we make them all positive by taking their absolute value, and that's called the absolute deviation. So the absolute value of negative 5 is 5, the absolute value of negative 3 is 3, and the absolute value of 8 is 8. Now we add those three numbers together and divide by 3 to get the mean absolute deviation. Mean, because we're dividing by 3, it's a type of mean, but it tells us the average or the mean deviation. So on average, how far away is a typical score from the mean? Scores are about 5.3 away from the mean. As an aside, if you were to calculate S for this problem, you would get 7. So it's another way of looking at the variation in a data set. You get different ideas of how the data is spread by looking at these two different measures.